Okay, we're gonna go ahead and get started. With that, what is the noise coming out of that speaker? All right, so with that, we're going to go ahead and get started. This is the NTP working group at IETF 124. We will start with the note well. All of the, this is the rules that and procedures by which we operate. You have agreed to these when you registered for the meeting. All participation in the IETF on mailing lists or in person must abide by these rules. And if you have any questions, feel free to talk to myself or Eric, who is our area director, sitting up here at the front. Dieter, my co-chair, is online. He will be taking minutes in the notepad that's linked from the agenda. So feel free to help him out by contributing any notes in there as well. Here's a few meeting tips that you may have seen in previous meetings this week already. For everybody here and well, obviously if you're online, you've already done this, but be sure that you scan the QR code to register your participation. You will not be able to get into the queue to ask a question unless you are in the on Meet Echo. So the and also, if you don't mind, if you could give your name when you speak at the queue, even though if you've registered through Meet Echo, we should have it, but go ahead and repeat it, please. With that, this is the agenda that we have for today. We have a pretty full agenda if everything goes according to the current plans. With that, we will, is there any agenda bashing? Nope. Excellent. So moving on, the first item is just a working group status of documents that are sort of beyond the working group at this point. NTP over PTP has gone through IETF last call and the IESG telechat. It still has a discuss on it, but that discuss is some additional text that we need on guidelines to provide to the designated experts for the registry. So it's just a couple sentences that we need to get pulled together, and then that document should be done and ready to go. Rough time has been submitted to the IESG, so it's in the first step of that process. And then the third document that I wanted to mention was the NTS for PTP. I know that it's still listed there as a working document. We are still planning to work on that document. However, we need to make some progress in the 1588 working group first. So it's on hold basically while we resolve some basic approaches in the IEEE 1588 security subcommittee with respect to how their piece of it is going to move forward. We are planning a face-to-face of that group in December to hopefully resolve some of these issues and make some progress in the near term. And a little bit later in the agenda, I'll provide a quick update of where the I-1588 work is. So those are the documents that are on our work plan that are not going to be discussed today. Does anybody have any questions about these three documents? Nope. All right. So the next item on the agenda is the update on NTP v5, Tal.
Okay, thanks. So my name is Tal Mizrahi, and this is an update about the NTP v5 document. Next, please. Okay, so these are the main changes since the previous IETF meeting. So we've had two versions since IETF 123. The main changes are, first of all, related to the MAC extension field, which was previously a pretty short section. It had references to previous documents, and now it's more detailed section, which includes all the details, more self-contained. That's one aspect. Another aspect is related to the NTP-v5 message format, which was slightly updated in order to be more similar to the NTP-v4 format. It's not identical, but it's a little bit more similar. Another aspect is related to the expired requirement document, and that's something we've been working on for a few months. We basically reviewed the requirement document in order to make sure that the requirements are aligned with the NTP-v5 spec. And there's a long list of requirements, and for each one of them, there's a kind of a note about whether it's included in the NTP-v5 spec or not. And we completed this work. We did all the necessary changes in the NTP-v5 spec. And now we believe there's no need to further process or maintain the requirement document. It can just keep on being expired. In addition to that, a few more updates and nits, which are relatively minor. Next, please. In terms of the next steps, what we'd like to do in the next few months, and these are issues that were mostly discussed on the list a little bit. One aspect is related to the reference ID extension field. And currently it uses a Bloom filter, which requires 512 bytes. That's pretty long. So Miroslav is working on a few possible directions of reducing the length of the extension field. And he suggested a few ideas on the list, but there will probably be more detailed ideas in the upcoming few weeks. So that's one aspect that was discussed on the mailing list. Another aspect is related to handling unknown flags. So there are a few flags in the message format, and the text wasn't completely clear about what happens when you receive an unknown flag or an unsupported flag, how to handle that. So there's probably a need to think about it a little bit and have more detailed text about how that's going to be handled. And some further clarification will probably be needed for the monotonic receive timestamp extension field. So these are a few open issues, nothing major here. So it's probably not a lot of work, but we are open in general to any feedback generally about the document. If anything is missing in the document, if there are major issues that we didn't think about that need to be addressed, this would be a good time to raise them, because assuming these three open issues can be handled in the next few months, once we do that, we'll probably want to go for a working group last call. So we're open to any comments at this point.
Go ahead, David.
Yeah, forgot to recently bring this up on the mailing list, but I think there's also still some work open regarding greasing for extension fields. And I think we should look at that before we go to the last call.
Okay. Okay, that's a good point.
All right. So we have something else to add to the list. I think this is a really important time for people to start reviewing this document. So if you could give it a read, I'd really appreciate it, and send comments to the mailing list. We do have a GitHub repo through the IETF org, so you can also submit pull requests there. So any questions on that? Nope. All right.
Thank you.
You're welcome. So next up is, I believe, David. Are you next on NT? I need to switch to the agenda tab. Hold a sec, but I think it's pools, NTS pools. Go ahead, David.
Okay, am I audible?
Yes, you are.
Good. So with NTS pools, over the last few months, we've been hard at work getting a completely working experimental pool up and running. We are now at the point where that is actually running, to the point where we have the pool itself running, we have management interface running, we have monitoring running for the servers in that pool. So it's basically at the point now that it's a fully functional pool. I'll send an email update later today containing all the information on where you can find that pool. But for those who want to look at it right now, it's at experimental.ntspooltest.org. We've updated the draft for that to match that implementation. There's been one major change, and that's that we've moved away from using TLS certificates for authentication and moved towards pre-share token authentication, just because it turns out that it's just a lot simpler to set up and deploy. Maybe we should have seen that earlier, but oh well. Other than that, the draft has been pretty much stable over the last months. There's been some minor textual edits. Thanks for those who contributed those suggestions for those. So yeah, we're at the point now where hopefully if people are interested, they can start adding servers to the pool. If you're implementing NTS, then this is also the time if you want to provide input with us on patches for your implementation, because we're going to do patches for most of the major implementations as well. If you want to provide input for how we can do that best, now would be the time to contact us. And please add servers, please try use the pool. Do note that it's starting out now with very few servers in it, so initially you might not get a disjoint set of servers, just so you know. Are there any questions at this time?
Are there any questions about the NTS pool experiment? Nobody? Okay. Thank you, David. And I believe you said, oh, go ahead.
Yeah, in that case, if there's not questions, then I think this is about the time where we would like to move this towards maybe doing an adoption call within the working group. Not sure if there's, I know there's been questions in the past about, do we want pools like this? The problems we're starting to run into is if we get something that becomes popular, we want to keep it running, preferably in the not too distant future. So we do want to aim at moving towards more definitive extension field types and a more definitive domain name. The latter is not something the working group needs to worry about, but the extension field types means that this specification for how the communication handles either needs to be published as a non-IETF specification so that we can use the specification required allocation process, or we need to have working group adoption so that we can use early allocation at that point. So the question becomes which of those two paths the working group wants us to take.
Do you, we would still, are you still interested in publishing it as experimental for now, or did?
Yes, okay. We would be interested in publishing it as experimental, but we do need the allocations at that point.
Right. It seems completely reasonable that we do a call for adoption on this document. Does anybody have any comments or questions, thoughts on proceeding with the call for adoption on this document? We have discussed for a long time that the pool NTP, the pool problem is a problem for adoption of NTS, and we need to be looking at various solutions to that. And this is the only one we have on the table at the moment. So, thoughts? More caffeine for everybody in the room, maybe? All right, so with that, we'll go ahead and do a call for adoption on the mailing list. Thank you, David. Excuse me? They want to do an early allocation request. And so if we do the call for adoption, we can do an early allocation request for a working group document. All right, so the next item on the agenda is for time synchronization over Quick. Let me switch over to, hi, Garrett.
Hello, am I audible?
You are audible. Let me just get your slides going here so I can.
Sure.
All right, so I have passed slide control to you, and you should be good to go. Thank you.
Perfect, thank you. For anybody that doesn't know me, I'm relatively new to the NTP work group and or just IETF in general. My name is Garrett McCullum. Today, I'm here to give a quick overview on the experimental draft of time synchronization over Quick. The goal is simple: to explore how we can deliver secure, accurate time using the same transport technology that already powers a lot of the modern internet. This is not a replacement for NTP or NTS, but more so a complementary experiment on using Quick as the carrier of time, right? So let's start with the problem that we're trying to solve. Why do we need to rethink time transport? Traditional NTP has served us well for decades, but deployments have become harder. UDP traffic on port 123 is often filtered, rate limited, or silently dropped by middle boxes and or firewalls. NTS adds security, but also adds another handshake, more state, and operational overhead. These factors make it tough to deploy reliable time sync in cloud, enterprise, and mobile environments. Meanwhile, Quick is already everywhere: browsers, CDNs, APIs, and it provides a secure multiplex congestion control channel over port 443. So the question is, why not deliver time using the same already secure transport? That brings us to what TSQ actually proposes. So TSQ is a lightweight protocol that runs directly on Quick. For those that don't know, Quick is, in a nutshell, Quick is this secure multiplex transport protocol that runs over UDP, which integrates TLS 1.3 encryption and supporting connection migration for modern internet applications. Since TSQ uses Quick's TLS 1.3 handshake for security, there's no separate NTS key exchange step or the key management channel. Messages are exchanged using a simple time length value TLV structure, flexible, easy to parse, and future-proof. The idea is that TSQ client and server communicate inside of a Quick session or over a new one using the same port 443. This way, time sync can piggyback on the secure connection applications already trust. TSQ is meant to complement NTP and NTS by offering an alternative path in environments where UDP is unreliable and or restricted. So how does this actually work in practice? So the operational model. In a basic exchange, a client sends a time request TLV to a server over Quick. The server replies with a time response TLV containing its timestamp. There are optional TLVs for metadata, just used as an example, like clock quality, leap second information, and or error codes. The experimental draft currently defines these three core TLVs: 247, which is a metadata query request; 248, which is a clock quality info; and 249, which is the error and or status. TSQ can use Quick streams for reliable delivery or datagrams for low latency one-way measurements. That flexibility lets us experiment with both precise two-way exchanges and lightweight one-way timing models. All this happens securely within Quick's existing encryption and congestion control mechanisms. Now that we know what it does, let's look at why Quick is such a good fit. So why Quick helps? First, security comes by default. TLS 1.3 gives us encryption, authentication, and replay protection. Second is mobility. A Quick session can migrate between networks without losing state, so time sync continues even as devices roam. And third, Quick zero RTT resumption enables nearly instant resynchronization after reconnects. The TLV registry keeps the protocol extensible, and there's no new port or additional handshake to manage. In short, TSQ makes time behave like any other modern internet service. Here's where basically we stand today with the draft. So the current draft, the experimental draft, defines the core framing, the TLV registry, and both stream and datagram operation. It expands the security text to cover quick resumption, replay protection, and multi-server querying. The main feedback areas we're looking for from the working group are: should TSQ reuse NTP's registries or define its own TLV space? What's the right timestamp encoding, the classic 64-bit or something Quick native? And what deployment models make sense, like as in standalone servers or embedded services within existing Quick apps? The next phase to this is to prototype, gather performance data, and work toward an experimental RFC. Finally, let's see how we can get involved. If this concept sounds interesting, please read and comment on the draft. We'd love to hear implementers test Quick stream and datagram modes and measure timing precision. Right? Feedback is welcome in the NTP working group list or directly via the data tracker discussion page. Thank you all for your time. Again, this is my first time here, so this is kind of a little bit of a milestone for me. And I appreciate everybody's feedback, whether good or bad. And if you guys have any questions at all, please let me know. I'm an open book. I'm trying to do my best here.
Thank you, Garrett. So we do have a queue. Tal, go ahead.
Hi, Tal Mizrahi, Huawei. So thanks for presenting this work. One question I had was whether you analyzed the resources required by this idea compared to using NTP and NTS, and how this would affect clients' servers in terms of resources, which would affect scalability naturally, and also whether these resource implications would affect the accuracy. So that was
sorry. No. As of right now, I have not tested it yet. Right. So I haven't put it to practice to actually see the resource usage that would basically what you're asking for. Right. Like effectively, if we have thousands and or tens of thousands or millions of NTP calls, or in this case, TSQ calls, would that basically correlate to it like what we have with NTS today? Or would it be more lightweight or heavier? Right. That's your question.
Right. Yes.
Yeah. As of right now, I cannot speak to that. Right. Because I have not tested it.
Okay. And one more aspect which I was wondering about is you mentioned port 443, and that's currently reserved for HTTPS. So did you intend for NTP to run over HTTPS? Was that the intention here?
Well, I mean, we use the ALPN numbers, so that's registered. So effectively correct. I mean, it would work over UDP 443, right? As opposed to like TCP. But yes, in theory, yeah.
So actually, there's an entire stack here of HTTPS over Quick, over UDP, and so on, right?
I would need to double check, but I mean, I apologize. Like just to late answer your question, like the standard Quick 443 with its own ALPN identifier, like so there would be like no interference with like HTTP3 traffic, if that makes sense.
Yeah,
like
that's the way this works. Everything is on 443, and ALPN is the new port number.
Right. Yeah. I'm sorry. I a little bit of pressure. Like it just makes me.
No worries.
Okay, thank you.
David?
Yeah, I'm just wondering, and this ties in a little bit to your next steps list as well. So if we could go back to that, that would be awesome. But whether we as a working group really should be pursuing something like this. And the reason why I'm a bit skeptical is it's taking us plenty long to get NTP v5 done. We don't really seem to be having that much capacity for review on these sort of things. So maybe at this point the feedback choices, it seems more logical to me to go do a number of these next steps in different order, and really do prototype testing first and see whether this is at all scalable at the sort of skills that would be needed for NTP NTS replacements, because I'm very skeptical on that one, given that typical time servers with very modest hardware run thousands, if not tens of thousands of time requests per second from that kind of number of parallel connections as well. So I really think that if this is really something that wants to be pursued within this working group, we need really solid data before we make the time investment as a working group.
Yeah, I don't think he's asking for adoption yet, so I think he's...
No, this is still experimental, right? Like I've yet to test. This is still just, I mean, I hate to say it, a thought experiment. You know what I mean? So yes, exactly.
I think we would,
like sorry?
Yeah,
I'm sorry.
I think we'd be interested in hearing how you go as you go through your prototype and interop testing, and then we can consider whether it makes sense to develop it at that point. That's a later discussion.
In that case,
like this. Sorry, David.
Yeah, and in that case, I would just say that maybe we should postpone any questions on registry alignment and timestamp formats and deployment models, really to the point where there is a prototype to look at and discuss. But just my 2 cents.
All right. So, Miroslav?
I would like to ask if you have considered like not inventing your own message format, but simply use NTP, like define this like NTP over quick, a new transport for NTP.
So, right. So like this was like when I effectively opened up this question to the work group initially, I opened up exactly that. Like, has anybody ever effectively like brought this topic up? Like, all right, have we even thought about transporting this over quick? And everybody said no. And then I forget which individual, I'd have to grab her name. I think she immediately filed an experimental RFC with quick as a transport model for NTP, right? And then I hurried up and got TSQ it. But I mean, I could pull up that experimental draft, but I would need to find it first. So I believe that there is an experimental draft for what you're asking.
Okay.
Okay, thank you. I think this would be quite a simplification.
Okay. Mark?
Yes, Marc Blanchet, can you come back to, I guess, the slides that says UDP, is a problem? Yeah. So I guess maybe you should qualify a bit more. UDP is a problem because Quick actually uses UDP, right? So,
right.
So therefore, if there's a problem with UDP, then Quick has a problem also. So maybe it's just a slide, but I guess there will be more, text to.
Right. I mean, I'm not saying like there's a problem inherently with UDP, right? So like I work in security, and me as like a security engineer, I know that majority of like 90% of like NTP issues are due to blocking of UDP 123 through a network, whether that be infrastructure, ISP, et cetera, right? Whereas typically UDP or TCP 433 are allowed by default, typically, right?
Right. What I'm saying is, either in the slide or text, make sure that what you just said, or, qualify
Oh, gotcha.
appropriately, because,
Yeah.
Okay, I apologize. I must have missed it.
Oh, no,
Thank you.
no, that's fine. Go ahead, Jeff.
Jeff Houston, I had one more sort of query around this same area of using quick. In UDP, the path is the kernel driver, UDP, dispatched straight into the application. In quick, it's the kernel driver, UDP, passed to the quick module in user space, and then go through the quick functions and then up into the application. Isn't that a problem? Because it introduces another round of variation and noise, because you're not working at the same elevated kernel interrupt status as you would at the kernel level. The quick implementation in user space is more prone to other things happening on that box. And if you're trying to jam this into restricted areas of application or sharing with other things, doesn't quick have inherent problems because of this nature, that the processing is no longer kernel based, but in user space?
That's honestly a great question. Yeah. That's honestly a great question. And like, honestly, from a high level, I can't really answer that, but in the same operational model, like we could look at like DNS sec, right? Or DNS over quick. And that same argument could be made towards DNS.
No, DNS sec is nowhere near as time critical as quick. DNSSEC can take an awfully long time before it becomes an issue. With quick, time is the subject, and adding effectively processing latency or jitter through the fact that you're operating up in user space is, I thought, an important consideration here.
Yeah, I'll definitely take that into consideration. Okay, I'll definitely have to get a prototype available.
Thanks.
All right. I thought there was somebody else in the queue, but they do seem to have dropped off. So thank you, Garrett. I would appreciate, I do think that this working group would like to follow your progress as you do the prototype and implementation type stuff. So please come back and tell us more about it, and then we'll see at some point later some later point in the future whether it makes sense to try and specify an experimental RFC. All right.
Yeah, thank you so much for your time.
Yeah, no, this is great. Thank you.
Thank you.
Let me hold on one moment. Take slides back. All right, Sarah, I believe you're up next on algorithms. Let me get your slides up.
Hopefully I'm audible.
Good morning.
Good morning.
So go ahead. Do you want to control them, or do you want me to?
If I could control them, please.
Okay. There you go.
Thank you. So good morning. I'm Sarah, and I recently wrote a draft that tries to describe algorithm use with NTP v5. There's several things I've covered in the document, namely general information for algorithm designers, such as the use of extension fields, handling of different timescales and leap seconds. There's also some very general and incomplete text about using NTP v4 algorithms with NTP v5. That's going to take a lot more time. I've done it as an informational with no normative language. I've also not included any formula or code or any other algorithm details just yet, but there's some questions I have about that later on to ask the working group. So why do I think we should do this? It seems that there's a lot of different people with a lot of different views in the working group that feel that this is necessary for NTP v5. And these are just some quotes that I've dug out of the mailing list and out of recordings of previous meetings that I think best summarizes those views. In addition, there is also some text that exists in both the current NTP v5 draft and also in the expired requires requirements document covering this particular topic. So it's kind of clear to me that the demand for this document is wanted and needed by the working group. And I have sort of 3 questions for the working group, and I would really like to hear people's feedback on this. The first one is if we're to have a document like this, do we need to specify algorithms, or is referring to NTP-v4's algorithms enough? Another question that I have is, do we need any normative text surrounding it? Or can we just produce an informative document? Would that be sufficient? And lastly, is there any topics that need to be included that are needed for adoption with the working group? Yeah. That's all I've got to say. David, do you have a question?
David, go ahead.
Yeah, so given that you have these open questions, I think I'd like to provide some input on point 2, and that is that, at least from my perspective, it was a very conscious choice to split the algorithms out, and that we should be very careful with normative text on, at least on algorithms themselves, because part of the goal with NTP-v5, and these were very painful discussions that I'd really rather not reopen, was to really allow implementers to make their own choices around algorithms and really specify behavior more than how you get towards that behavior. So I think that needs to be an area where we tread really carefully.
Well, one of the other alternatives she provided here was to reference 5905. I don't know that that's what we necessarily want to do either, do we?
No, look, I think we should stick to the plan that was mostly agreed on in the preparation process for NTP-v5, which is the choices around implementation around algorithm are implementation specific.
I don't
which
know that.
matches current things.
So-
and I would not refer or go for a specific specify a specific algorithm.
Right.
in
The
any way.
discussion around NTP-v5 was that we needed to separate the algorithms from the protocol, not that there would be no algorithms.
To be clear about this question, in the current NTP-v5 document, we have this text in the top section that says that clients may use NTP-v4 algorithms. So it's already being referred to. And so what I mean in my question about referring to it is doing much the same as what the authors of the NTP-v5 draft have done, and perhaps going into some further detail, for example, covering the errata that exists for algorithms within NTP-v4.
Go ahead, David.
Yeah, I don't know. I don't have the particular expertise in that specific algorithm, and the unfortunate part is that the 5905 just doesn't sufficiently constrain it to fully define what the NTP-v5 of the NTP-v4 algorithm really is. Like there's gaps missing there, which in the past, at least, Harlan has made it clear that he considers sort of the actual implementation in NTP Classic to be part of that specification, even though it formally isn't. So, and I don't know if we have currently anyone who's who is familiar enough with that suite of algorithms. And the secondary question that you can ask is it needed for implementers? To take a comparison from the IEEE, if you look at the P2P specification, there's just no discussion of algorithms there at all. And they seem to be doing fine on the implementation front. So perhaps that's also something to consider. Maybe rough guidance or some references to papers might be sufficient. Like there is a decent pool of research work on this in the scientific literature that could provide input to implementers if they need it.
Yeah, I wouldn't characterize what 1588 has done as have no algorithms. I think what happens is you see a lot of that behavior specified in the various profiles. And so there's plenty of pages of specification related to profiles and behavior that you expect in profiles. All right, is there any more questions on this? All right, thank you, Sarah.
Just as a quick question, next step, should I take these questions to the list to get a bit more feedback? Or
yes, it would be helpful if you explicitly ask these questions on the mailing list.
Okay, I'll do that. Thank you.
All right, thanks. Let me take control back and up slides and share slides. All right, the next all right, so timestamp extension fields, go ahead.
Hi, everybody. My name is Yu Tang. Same as Garrett, this is the first time for me to join IETF, so it took me some time to figure out how things work. All right, so Karen, if possible, then could you please take the controls, make sure that I'm not doing something.
Oh, I'm sorry. I just passed control.
No, I see the control button here, so let me just try. If it doesn't work out, then you can take it back. All right, okay. So today I'm going to talk about something related with the NTP v5 timestamping extension field. In NTP v5, and it was really proposed to separate the time and frequency offset. And we find that as a brilliant idea because we work in a very similar field. And it was protocol-wise, it was recommended to use monotonic receive timestamping. So that basically, if a client received a timestamp from the server using this monotonic receive timestamp, then it can somehow use this timestamping to recover frequency information between a client and server pair. But we have to notice that in Linux, there are actually a number of clock sources that people can find. So the monotonic receive timestamping obviously uses the clock monotonic source, but it basically behaves quite differently depending on how NTP adjusts the time. For instance, if NTP adjusts time by stamping, meaning that by making the time jumping forward or backward, clock monotonic is not impacted at all. But as long as the system clock is slowed, then clock monotonic would be impacted at the same rate as clock real time. That means that it cannot really preserve the true frequency on from the crystal. Note that we also have an additional clock source, which is called clock monotonic roll. And this is not really often used while doing time synchronization, but it has a very nice characteristic that means that the frequency of this clock increases monotonically. So despite how you want to change the system clock, it preserves the frequency quite good. So in that sense, it seems to be a better choice in terms of frequency transfer. And not only about that, because we did a little bit investigation on this, and we find that this particular time clock source would basically allows easier implementation and also enhances the synchronization accuracy. I will be a little bit faster here. So as people were discussing, colleagues are discussing in NTP v5, there's no algorithm being specified. So to compare the performance of this two timestamping, then we did a little bit from our side. We implemented two versions of implementation of algorithms for monotonic receive timestamping. And for the monotonic raw timestamping, we proposed two different versions. And if your network is quite symmetric, then we propose to use monotonic raw receive timestamping only. However, as long as you see that your network noises becomes asymmetric, then adding an additional timestamping from the transmitter side would really helps you to improve the accuracy. So on this slide, I'm going to briefly talk about the first implementation. So the first implementation about monotonic receive timestamping, it's quite in line with a very brief description in NTP v5. So how do you want to use this monotonic receive timestamping? It's quite straightforward. When you receive a monotonic timestamping from the server, you kind of like uses the difference between the two consecutive monotonic receive timestamping, because this gives you the difference, the offset basically caused by frequency drift. And if you further do the difference between two consecutive timestamping from the real-time clock, then you have the offset caused by NTP adjustment as well as frequency drift. And if you further make the difference of those two values, then you got the proper amount of offset, which is caused by NTP adjustment. This looks a little bit complex, and yes, we agree this implementation is a little bit complex, but the key idea is you use the monotonic timestamping to correct the offset, because NTP is making adjustment and you want to correct it from the server as well from the client side. So here, if you follow the flow here, then you would really, if you do everything properly, you would be able to keep track of the offset, which is caused by NTP adjustment. And we call that value as theta correct. And from the theta correct, if you collect multiple samples, you can either use linear regression or whatever techniques you want to use to estimate the frequency. For the second kind of implementation, we use a simpler version. We say that, okay, since you want to use monotonic receive timestamping to correct the offset, then why don't you use it to correct the timestamp? So here, then you would have a much easier implementation. For the real timestamping, you just use it to estimate the offset. For the clock monotonic, you use it, and you try to keep a virtual list of the timestamping, because every time if you lose the clock, you know that, okay, what is my previous frequency, what is the frequency that has been slowed, and in this way you could kind of like compensate to the timestamping, and you would really maintain a virtual correct monotonic timestamping, and in this way you could recover the frequency correctly from it. This implementation is actually much simpler than the one before, but if you take a second look at it, then you see that, okay, I'm maintaining an extra list of monotonic timestamping, and why don't I use a monotonic raw clock instead? Because with monotonic raw, and you don't need any correction. If you simply read from that timestamp, it will just give you the correct or the true frequency from a node. And now I'm basically rephrasing what I'm just talked about, what I just talked about with monotonic raw clock source. You don't need to do any correction. So in this sense, you still keep the same flow as I described before, and you want to read not only the the monotonic raw receive timestamping, but also you want to take a record of your local timestamping when you send a synchronization packet. So if you have that, if you have T2 and T1 in terms of monotonic raw clock, then you do the difference with T2 minus T1. You can basically infer or estimate the frequency out of it. And on the right side, I give a very extreme example where basically this is a true measurement from one of our production network. And we have a very, very extreme asymmetric network where the forward and backward path is completely different. So here then we would recommend to use the monotonic raw transmit timestamping, and you would use another measurement point, which is called T3 minus T4. And by using different filtering algorithm, you can filter out those anomalies properly, and you could reduce the errors caused by asymmetry, network asymmetry. All right, so I will speed up a little bit because to verify what we have explained before, we did two types of experiment. We implemented both of the implementations on a simulation platform. We also did an experiment on a real test bed. So in both cases, we evaluate a network with 11 hops, and we see that okay, here in this slide, you see the performance of monotonic receive timestamping in a noiseless environment. So there's no noise, and if we have implemented everything correctly, you see that okay, with monotonic timestamping, we can eventually recover the frequency properly. It's only that it takes quite a long time to converge. Somebody switch off my light. I'll keep going. All right, okay. Am I on the right slides? Okay, but as long as you introduce noises into the network, here we introduce a little bit of the Gaussian noise. And with Gaussian noise into the network, then we find that with monotonic raw monotonic receive timestamping, the errors would be quite large because we consider here from time point 15,000 until 30,000, the system is more or less stabilized. And here you see that the errors would be, the frequency errors would be maximally 25 ppm something. So on the other hand, if we go to a monotonic raw timestamping, the frequency is quite stable and it doesn't really impacted by slowing the real time clock. So the frequency that we have recovered is quite stable, and on the last client, the maximum frequency error is reduced to 5. So it's like a 1/5 reduction on the error. Here, we did the same experiment, but on a real test bed. Here we run Crony version 4.8. And here what we did is we introduced even a bit different type of error. So we introduced background traffic between each of the servers. And the background traffic can go either forward or backward or in both directions. And we try to simulate both symmetric and asymmetric network scenarios. What is important is here from the first and the last server, we applied IEEE 1588 as a benchmark, and the time error is computed as a difference between the ones from Crony and 1588 or from monotonic raw with 1588. So here I would actually quite willing to discuss with Miroslav. Strangely, we find that at the last server, Crony fails to converge in terms of the frequency. It always oscillate and oscillate. And while using monotonic raw, on the other hand, allows the system to converge, and the error bars is quite small. But I have to remind you, the error is reduced to 0.0 something, not only because of using the monotonic raw timestamping, but we also applied a little bit advanced filtering technique. But it still doesn't explain why the frequency offset from Crony fails to converge. Okay, I still got 2 slides, and for the second last slides, I want to talk about an additional field which can help the system to converge faster, and we name it as frequency to the root server extension field. And this is a bit more like the cumulative rate ratio defined in PTP, only that we use this one, we use the extension field that we defined here as a means to expedite the convergence of frequency offset transfer. So what we want to include is 32 bits with the first bit as like a sign bit. So it basically indicates if a node is running faster or slower compared to its upstream node. And for the remaining 31 bits, this takes the absolute value of the frequency difference or frequency drift between 2 pairs. We did also an experiment on this, and the effect is quite obvious, because without such a field, a node would only start to converge or try to converge to the root server once its immediate upstream server is synchronized. So this takes long, but as long as such an information is carried in the synchronization packet, then everybody would be able to start to synchronize to the root quite early than the one without it. So here we see a performance difference of half of the reduction of the convergence time with and without using such a field. And we think this could be an interesting thing that to be included in NTP v5. And that's all from my side. And if you have questions or discussions, and I'm happy to be involved.
All right, thank you. Before we start with questions, the draft was submitted. We had a little bit of confusion about getting it submitted, so it is online now, and it is a new draft submitted. So go ahead, David. Concise, please.
Yes, I was wondering, you were saying that if I read the standard correctly, the monotonic clock timestamp that's supposed to be included in the monotonic timestamp extension field is not supposed to be corrected at all for phase. So it's frequency stabilized, but not time stabilized. Why? What is the difference? So you seem to be mapping Linux kernel clocks, which do not necessarily match here. But then I don't think it's intended to match the monotonic clock of Linux, which is frequency and time, as long as you only do slews. But it's really intended to match a just frequency corrected clock. So what exactly, if that's the case, what is the advantage still of having something separate for the raw clock, which is random frequency, whatever else is out there?
First of all, the monotonic raw clock time, it doesn't really have some random frequency. So the frequency is preserved always monotonically. So it's not really impacted by any adjustment. So from that point of view, it's more stable. While if you use clock monotonic and if you slew the time, then clock monotonic would be driven by the same rate as clock real time. So that means you might lose the accuracy of the frequency that you want to keep. And this might introduce additional errors to your network and reduces also further the synchronization accuracy of the system. So that's why we are not really demanding, let's say, to use monotonic raw clock, because it's not really everywhere supported. So what we want to say that if a system supports clock monotonic raw, then we encourage the usage of such a clock. And using such a clock, you would have a simpler implementation, and the synchronization accuracy would be greatly enhanced. Did I answer your question, or I didn't get what you really want to say?
No, like I'm having a bit of trouble with the difference between like the actual model of what you want to send versus what matches with the Linux clocks, because monotonic raw, in my experience on real hardware, is definitely not a stable frequency clock, especially once you go towards more lower end hardware. But we maybe discuss after Miroslav has asked this question.
Yeah, we can discuss also this from the mailing list.
Go ahead, Miroslav.
Yeah, I wanted to point as David did, that the draft says, I think, that the clock that's capturing the monotonic timestamp, it's not supposed to be impacted by phase correction. So that excludes the POSIX monotonic clock, I think. So in your tests, if you were using that clock, I'm not surprised that it didn't work well.
No, on POSIX, no. The POSIX doesn't really support monotonic raw, no.
The Linux monotonic clock is the POSIX monotonic clock, I think. So
well,
that is impacted by phase corrections, and that's not a good clock to be used for this monotonic timestamp in NTP 5.
If you're talking about in Linux and then talking about Linux monotonic raw clock, in our experience, it's quite stable. And I don't really see why the statement that you say that it's not really good for frequency offset transfer, because we've done a number of experiments, and there it runs always quite stable and not really impacted by any slow or stepping.
You mean the raw monotonic clock?
Yeah, whenever they are, yeah. If
Okay,
they are monotonic, yeah.
The monotonic raw is not impacted by the phase corrections, but its frequency is not stable because it's the hardware frequency that's impacted by temperature changes. So
Yeah. You are completely right. Yes. Yeah, not completely right. So what we have always assumed here is that during a certain amount of time, then the frequency is linearly growing. But you are completely right. If the crystal, the frequency from the crystal is impacted somehow by temperature or whatever, then you kind of like need another algorithm to rematch the frequency, to estimate the change of that. Yes, that I completely agree. And that part, well, we didn't cover it yet.
yeah, so the NTPv5 draft requires that the clock that's providing this monotonic timestamp is stable in frequency, it's not impacted by phase correction, and the frequency is accurate. So I think an improvement that could be made here is to allow a clock that is stable, but its frequency is not correct, like when you have a local standard using possibly an atomic clock or whatever. So I think that could be a new extension or maybe a flag in the monotonic timestamp that would tell the client that the frequency is not accurate, so it wouldn't try to like match it with the other clock.
That could be something that we could do, but we also so coming back to the stability of the frequency of the clock, that we find clock monotonic, the frequency is also not quite stable, isn't it? If it always changes. If you want to slow the clock, then the rate also changes, same as clock real time, and that's why you need a lot of corrections to compensate for that. Yeah.
Neither of these two clock, I think, is suitable for frequency transfer.
Okay.
Yeah. We also, you're right. We also considered to use a little bit more the atomic clock, which is a little bit more stable. But from that point of view, if you have a clock whose frequency is stable, I mean the crystal frequency of the crystal is quite stable, and then you could also option for a monotonic raw in this sense.
All right. Can we? I was wondering if we could move this discussion to the mailing list. We're running short of time. Thank you very much. So the document has been posted. I think people should take a read through it and provide some comments. Um, all right, so the next, I hope I have the right version of this. So this was a presentation given at RIPE, and I asked him to come and present to us as well. Let me pass slide control to you. And there you have it.
Yeah, perfect. It works. Thank you, Karen. Thanks again for inviting me to this meeting. So hi everyone, my name is Shreyas and I recently graduated from TU Delft in the Netherlands. And today I'm gonna present my work which I did for my master thesis. This is also my first IETF meeting actually. So today we'll talk about a bit of introduction, the baseline behavior of clients, and some attacks I did on them. And I also want to mention that this project was done in collaboration with SIDN Labs and Tweetegolf in the Netherlands itself. Yep. Okay. So introduction. I'm pretty sure everyone over there, over here knows NTP, and it's very essential for clock synchronization, and a lot of protocols are dependent on it. It has become the default for timekeeping on the internet and can provide accuracy in the terms of milliseconds over the internet. Yeah, the latest version was the NTP v4, which was introduced, standardized in 2011. It added better algorithms, kiss of death mechanism, and in 2020, a new extension, like the NTS extension, was added to improve integrity of the packets. So since the days of DDoS, since the DDoS days of NTP in the early 2010s, a lot of research has been done on the NTP and the server pools, etc. But most of the research has been focused on the protocol itself and the servers. Very little work has been done on the client side. That is the client's users actually using. If this piece of the puzzle is vulnerable, it's overlooked, it can undermine the best of server networks, the best of protocols. If the developers of these clients are taking any shortcuts, it's going to undermine all the hard work everyone at IETF is doing. These guys are this NTP client is the final judge in time synchronization. So in total, I tested out 8 different clients, and I took 3 system defaults from macOS, Windows, and Ubuntu. Yeah, just a quick summary of what we'll discuss. I measured the behavior of 8 different NTP clients under completely normal conditions, and after that, I exposed them to 2 different types of attacks. Yeah, so before we get to any attacks, let's take a look at how different clients available to users operate in the real world. We want to analyze how often do they query servers, how many servers do they use when they have multiple options, and how does it compare to everyone else. So talking about my setup, I created a virtual environment using virtual machines, and which was completely isolated. Within the environment itself, I had 3 NTP servers, which were synchronized with external time sources. All of these, these servers were behind an IP address, and all the clients were configured to use this specific IP address. This is most realistic of real world scenarios because most of the clients are configured to use a domain address, and the local DNS server routes them to the nearest NTP servers. So I ran these clients for about 6 years and collected the traffic. And it turns out there's a wide variation in the behavior of all these clients. SNTP clients, for example, send significantly less queries, and they also have a fixed polling rate, which means they send the frequency between packets is fixed always. NTP clients, on the other hand, showed a wide variety. The NTP-D, which is considered as the reference implementation or the closest one to the reference implementation was significantly lower at about 12 packets an hour, and all the way up to 250 packets per hour, which is the NTP DRS, which is developed by Tweeter Golf and written mostly in Rust. More packets generally means a better accuracy, and many clients do analyze network conditions and based on the latencies and the network jitter to sometimes send more or less packets. So the previous graph was aggregated on 3 servers, as I mentioned. If we split the data across the 3 servers, firstly we see most of the clients uh, utilize all of the 3 servers available more or less equally, except if you go all the way at the last, the time sync D, it uses only a single server. If this usage of single server can become a single point of failure for that client, if in case that once a chosen server is unfortunately malicious or even like malfunctioning anyway. The RFC for SNTP, the specification for it says it should the client should only use one server at any given point of time. But macOS and Windows are also SNTP clients. Yet they are utilizing all of the servers at the same time. Not at the same time, overall. We did inform this weird behavior to the developers, but according to developer, this is the intended behavior. And if the user wants higher accuracy and more reliability, they should be using other clients. If it on the all the other NTP clients, the normal NTP clients generally utilize all the servers, use all the servers all the time. So this is a time series showing the polling rate of two clients over the period of 6 years. The top one is an SNTP client. Top one is an NTP client, and the bottom one is an SNTP client. For the NTP client, we can see the polling rate starts off low around 4 and goes up and down and keeps on changing throughout 60 hours. But SNTP, on the other hand, we can see it stays the constant forever. Over 6 years, it's just the same. And in this case, timesync D is only using a single server. So timesync D was the default time client for Ubuntu, but Ubuntu will be stepping up its game and it will switch to using NTS by default. But NTS packets are significantly larger than normal NTP packets. And Ubuntu generally operates their own pool and operate their own servers. So we worked with them for a bit to analyze the increase in network traffic they would see. And turns out it's a significant rise in number of queries. It's a 25 times increase in the amount of data transfer and about 11 times increase in the number of queries. This is a significant rise in both the number of queries and the network traffic. And it turns out the people at Ubuntu had not thought of this. And we did notify them, and they are slowly rolling out more servers with this update. So now we move on to the attacks. Sorry. Yeah, so in time shift attacks, the attacker tries to manipulate a client into changing the time. If your system clock is wrong, many of your dependent protocols will not work. This is a screenshot from my browser, where it thought it was 2014 and refused to do anything. A few years ago, in 2012, there was an incident at the U.S. Naval Observatory's NTP servers, which were I think Stratum 1 servers, and many services and many all the servers dependent on this specific authoritative server had faced disruption and outages because the NTP servers at this location had an issue and they reported a time incorrect by about 12 years. This is one of the most feared situation for network operators. So NTP tries to fight back by specifying a panic threshold, which defines a maximum allowed offset. The recommended value is around 1,000 seconds, and in this experiment, we try to force the client into changing the time beyond this value, and seeing how it resists it. For the threat model, in our threat model, we control the NTP servers, and all the clients are redirected to the attacker servers. This might seem a bit difficult and bit impossible, but this scenario, this situation can be achieved if an attacker adds malicious servers in the NTP pool, or by hijacking the local DNS servers. So SNTP clients, turns out, are all vulnerable. Again, these are the default clients for all the major OSs, which means billions of devices are affected. But there are minor differences in how much time it took for a successful attack. macOS, for example, took about 2 hours for a successful attack. TimeSyncD was like 15 minutes. Like a few packets later, it had changed its time. Windows, on the other hand, took a very long time, about 36 hours. Plus, Windows does have a specific a, s- a specific panic threshold in place of about 2 weeks, because any time shift attack over 2 weeks was not successful. Fortunately, none of the normal NTP clients were vulnerable, and they resisted time shifting attacks completely. So next one is the kiss of death attacks, where we exploit the various kiss of death packets into cutting off clients from servers. It was introduced to protect servers from aggressive clients with V4, I think so. But it uses the same packet structure, and follows. It has the same inherent limitations of NTP, which is UDP. Uh, an attacker can abuse this feature by sending spoof packets to the client, and make it think that the server is telling the client to slow down or completely stop synchronization. Uh, so the best practices for NTP, which is the 8633, still recommends honoring these kiss of death packets, but it says the client should only honor them up to a certain limit, so that the clients are not completely cut off. And we try to manipulate these clients into stopping synchronization and seeing how they uh, react to kiss of death packets. We followed the same setup from the previous experiment, where the clients are configured to use the attacker servers, and the servers respond with two different kiss of death packets. The rate one, which says the client should slow down, and the deny, which means the client should completely stop. And fortunately, in this case, the results were positive, mostly positive. Most of the clients did ignore or did not care about the what the kiss of death packets were, and were completely unaffected. This is a case where the developers are deviating from the established standards, but in this case, it is actually benefiting the user. Uh, we encountered some minor bugs along the way. The NTP DRS accidentally sent 500,000 packets, which is about 6.5 million queries an hour, when it for the deny packets. Fortunately, this was a bug, and this was quickly patched. NTPD had a anomalous behavior where it stopped when it was told to slow down, and it sent too many packets when it was told to completely stop. Coming to the conclusions now. So all the three major OSs, Windows, Ubuntu, and macOS, all are using SNTP clients. Ubuntu, fortunately, will be out of the list very soon. We recommend both macOS and Windows deploy stronger NTP clients, or at least add some sanitary checks. Like OpenNTP has a constraint feature, where it does a sanity check with a HTTP server just to make sure it's getting the right, just to verify the time of the NTP servers. And every systemd based Linux distros should reconsider using timestamp and switch to more robust alternatives such as Crony or NTP DRS. Yeah, so NTP lurks around in the background of all modern computer system. It plays a key role in its well-functioning, and the defaults for major OSs are vulnerable, which is creating unnecessary risk for billions of users. If you want to read the full tech report on the full with more data and more fancy graphs, you can use this QR code. You can also contact me on this email address. And thank you very much. If you have any questions, please.
Go ahead, Miroslav.
In that test of how much traffic the clients generate, was that done in a local network or over internet?
It was the local network itself. I created a virtual environment and ran all the experiments virtually, completely isolated.
Okay, I think that may have impacted the results because over internet there are larger delays and the polling
yes.
interval would be adjusted.
So yeah, they can. So the results I got would be considered as the best case scenario. So if yeah, they can be considered as a best case scenario, but over the internet, I don't know how different it would be and how significant the difference would be. It would be different, but I'm not sure of the significance.
Yeah, I think, well, at least what I've seen, I think you had a high rate from Crony as a client, much higher than with NTPD, and I think that wouldn't normally happen over internet, like with the usual jitter. And in local network, yeah, that might happen.
Yeah, well, at least then we can like also see like in optimal conditions, the clients do send out more packets, which generally leads to a slightly better accuracy.
Yeah.
All right. Thank you very much. If anybody has any questions or follow-up feedback on their study, feel free to reach out and contact them. And thank you for coming.
Thank you. Thank you again.
So the last agenda item we have is just a really quick 1588 update. Just to keep you all appraised of what's going on in 1588. Just as a refresher, the key relationship between the IEEE 1588 group that does PTP and us has to do with the security and the NTS work. The current 1588 security is the authentication TLV specified in 1588-2019, and there is an amendment, 1588D, which adds some additional information on GDOI. The current key management options that are possible for PTP or that have been discussed are the static, GDOI, Tesla, and NTS. Amendment D provided additional information on the GDOI. Tesla, we really need some more details, but we're waiting for people to come forward and say they're actually using this. And the NTS work is what we're currently working on. The current work items for 1588K is to address the 1588, the PTP vulnerabilities that we've talked about here before, and to make some updates to the sequence ID. Also to add NTS as a key management scheme, and there's multiple proposals being discussed and with progress being made, and hopefully significant contributions soon. This other thing I've mentioned about previously, I wanted to remind folks again, is that there is a new effort ongoing in IEEE 1588 called CSPTP. This has a starting draft, and there are discussions on various updates. There is a plan to incorporate security into that initial draft, and that security will be based on NTS. There's an initial proposal on the table on how to use NTS for CSPTP. And then the work that was done at the hackathon in July, there was some preliminary proof of concept work done. So all of that is based on NTS. It is currently expected that that will involve no updates to NTS in the IETF. So all of the documentation specification related to that will be done in IEEE 1588 with no modifications to NTS. That's the current plan. And with that, are there, oh, the other thing I was going to mention is that there is going to be a face-to-face with respect to the use of NTS for PTP at the 1st of December, a small working team meeting to discuss that. So hopefully by the new year, we'll have an update on that and begin moving that document forward. I think I mentioned that at the very beginning of the meeting. So with that, we are at the end of our agenda. Is there any other business? All right, with that, thank you everybody for coming, and have a good day.